So we started last time a third way to store tree data structure, which is by, so type 3 is this orange example. So from any node you can go to the parent and keep on moving to the parent till you reach the root. So that information is stored in the array A. Okay, so parent of 0 is 5, parent of 1 is 5 and 5. So when fixed point, that fixed point root. So this exactly stores the tree data structure, and immediately you see an application of it in the question of data structure for disjoint set where the operations are union and find. Okay, so you start with initial sets, singleton sets containing 0, respectively 1, respectively dot dot n minus 1. So n sets, you start with that and then you are allowed to take union. And the other query operation is, so union is a update operation, and same set is a query operation, which is just to check whether I and j are the elements of the same set. So you want to do everything in log n time, right? So there are simple implementations, but they will take n time. So how do you do this in log n time? So what we will do is, let's go to the final implementation. So what we will do is we will store the sets, disjoint sets, as these trees of type 3. So 2, 4, 6 is a set, 1, 3 is a set, and when you are asked to take union, and the union operation was for 4, 3. So when you are asked to do union 4, 3, so 4 is an element of first set, 3 is an element of the second set. So you will find the root of 3, which is 1, and change its parent from 1 to 2. Okay, so you will get the 2, 4, 6, 1, 3 structure. So the pseudocode is there for fast union. The question is, why is the height of these trees log n? Right? So find essentially travels the height. So we have to show that the height is small. So why is it log n? Any ideas? How will you show log n? So somewhere you have to show some doubling is happening. Okay, so for that we have to recall that in the pseudocode what we did is we introduced a check that the smaller tree will be hooked to the bigger tree, right? So the size is what is kind of changing in a systematic way. So we'll use that property to prove log n. So consider a tree, which means it's basically storing a set rooted at node IT of height t. So let us draw that. So IT is the root node, and there is some subtree structure, but we'll just take the longest path possible. So that child is IT minus 1. And so on till you see I1, and then I0. Well, I0 will be, I think, just a leaf. So the edges here are, this is edge E1, E2, and this is ET. Okay, so this is the longest path which takes you from leaf to the root. Root is IT. Now we want to show that this, the T here is log of the size and not more. So why is that? So for that, some information is needed from the fast union pseudocode. Okay, so what, when do you think E1 was added? Was it added before E2 or after E2? Remember that your initial sets were singleton. So this means that sometime a union must have happened and E1, E2 would have been combined in the single tree. So what was the order? Yes, so if you can observe that from the pseudocode, it's good. So E2 was, so E1 was added before E2 in fast union. Right, so a sequence of fast union and same set were called, and sometime what happened was this E1 got added, and after that E2 was added in the second call. So maybe we should prove this just as a warm-up. So say E2 was added first. So if E2 was added first, then the problem will be that now I1 has become, I1 cannot be the root of whatever that tree is. Right, I1 is necessarily below the root. So if it is not the root, then how can even edge be added by fast union? Because fast union always hooks to the root of the bigger tree, right? So that is the contradiction. So this means that I1 is not the root. In any subsequent step. So once I1 at this point is not the root, it can never become the root because we never delete anything, right? So at no subsequent operation will I1 be a root from now on. So which means that E1 can't be hooked by fast union. Okay, so that is the contradiction. So this contradiction means that first union will add E1, and after that E2, and then after that E3, and so on. Right. So the order of union goes from E1, E2, dot dot ET. Okay, this is the strict order. in the middle, other things may be happening, but at least this is true that E2 can come only after E1 has been added. So addition order using the last code, fast union. Okay, that's the statement. And so now we are ready to finish the proof. So let me say that Tij size is the size of the tree with ij as root. And what I want to claim is, I want to relate size of Ti1 with size of Ti0. What is the relationship? Which one is bigger and by how much? So the claim is that T of I1 is bigger than T of I0. Do you believe this? Because E1 was hooked by fast union, so when it was hooked, then the tree of I1 must have been bigger than I0. But then I0 was added, right? So when you add it, it means that now the size is actually double, at least. Is this clear? So this is another property of union, or the pseudocode that we have written, fast union. So here we are using the property of size, that the tree is hooked looking at the size. So since the Ti0 is the smaller size, when you hook it, the overall size now doubles at least. Okay, so since the smaller one is hooked to the root of the larger one, the final thing is at least double. That's all we are doing, and which gives you the following sequence. So for all j, Tij is at least double that of Ij minus 1. Which means what? So if you cascade this, so Ti1 is at least double of Ti0, then Ti2 is at least double of Ti1, which means it is at least 4 times Ti0. Right? So cascading will give you that size of Tit is at least what? At least 2 raised to t. Okay, so cascade this t times, you get power of t there, power of 2, which is 2 raised to t. And what can this size at most be? This cannot be more than the number of elements, right? So what you have learnt is t cannot be more than log n. Okay. So this is a simple proof, but it is using this clever step which we did in union. Okay, using the size. So what we have shown is that height of any tree in this forest of sets, collection of sets, is at most log of the number of elements, which is n. And now, as we did last time, you just analyze, just look at the steps of fast union. The most expensive step is actually find I and find j, and that is now bounded by log n. So that gives us the result for union of disjoint sets. So theorem by Galler and Fisher. So set data structure operations. Take order log n time. And how much space? Only linear space, right? N is the number of elements across the sets. Is that clear? So this finishes the set data structure with operations of union and find. But this is not where the theory stops. There are actually much faster algorithms for this, for which you have to do some more advanced courses. So that we leave as a reading exercise. So one trick that you can use is called path compression. So what this does is that when you are doing find I, this path which you which find I will travel, every node in that path change its parent to the root. Okay, so that will drastically reduce the, I mean, it may or may not reduce, but the expectation is that this will help in making the tree of a lesser height. Okay, as the operations proceed. So path compression is find I has the side effect of making every node in the path that it travels, a child of the root. So simply drawn, it is this is what happens. So below IT you had IT minus 1, and below IT minus 1 you had IT minus 2. So change the parent of it, directly connect it to the root. Okay, so all these nodes which were there in the path traveled from I0 to IT by find I. So let us say this is find IT. So when you did, well, not find IT, find I0 maybe. So when you called find on I0, the path which takes you to the root, which is IT, is I0 I1 dot IT. So as you are traversing that path, in the end what you can do is just disconnect these and directly connect them to the root. Okay, so this is a trick called path compression, and this gives some amazing improvements to log n. So it significantly improves. To something called log star n. Okay, so this log star is it's a crazy function. It's basically the number of logs you can take of n to get to 1. Okay, so if n is 2 raised to 8, you take the first log, so you will get 8. Then you take another log, so you will get 3. And then you take another log and you will get below 2. So you will get close to 1. Okay, so log star of 2 raised to 8 is, for example, 3. In other words, it is the power of 2 that you are it's a tower of 2s. So you are looking at 2 raised to 2 raised to 2 raised to so on. Okay, so you want to write n like this. So how long this tower or how big this tower should be so that you get n or close to n. So that is log star n, so it's very, very small. So this data structure that you have seen, and so it is so easy to implement, it's actually almost constant time. It's almost order 1 for all practical instances that you will ever see. But we cannot do this. This analysis is too complicated for you. So the brave ones can read it on their own. The code is essentially this. So any questions? Because then we'll change the problem. Okay. So what we will do next is instead of designing these data structures, we'll go back to a problem which we want to solve in a very clever way using recursion. Okay, so again a very strong application of divide and conquer. It's an important problem. It's a problem of ith statistic. So to put it simply, you are given an array of integers, you want to find the median, and the array is arbitrary, so it may not be sorted. Okay, so array of size n, how fast can you find the median? What is the brute force? You have to sort, right? So you sort and then you find the median. In fact, you can find any ith statistic or ith minimum, right? So that will be time order n log n. So the question is, can you do it faster? Can you solve this in few scans, so which is order n time? Okay, it seems impossible because even for median it is not clear, and here we are asking for the ith smallest element in that array of integers in linear time, right? It seems or nearly impossible. But we will do this by a very clever sequence of arguments. So in the input you are given an array A or array S, n elements, n integers. Let's say they are distinct, but it will not matter. And in the output you want ith smallest integer. Right, so it is no big deal if you can sort. So you can just sort S and then output whatever you are asked in order n log n time. So this would be the brute force algorithm. Question is to do it in linear time. Okay, you want to save even on the factor of log n, which sometimes can be a big saving. So you want to do it faster. And in fact, ultimately, we want to do it in linear time, which is the demand which seems impossible to meet. Can you solve this in time order n? So this has a very famous solution. It was famously solved by a sequence of famous computer scientists. So Blum, Floyd, Pratt, Rivest, and Tarjan. In linear time. Okay, and the solution is by divide and conquer, but it's very clever, and it will introduce a new concept as well. And it's easy to implement, so we'll do this in detail. So let us call this function that we are trying to design select s comma I. Okay, so input output is the same. So input is given this array s and number I, and in the output you want select si will output the ith smallest element in the array s. No assumptions on s are made. So you want to design this. So what we want to do is we want to do something like quicksort. Which means what? So quicksort, the idea is that there is a pivot element which you choose arbitrarily or probabilistically or by some mechanism. So that pivot element is x, and then you partition s. S is an arbitrary array, no assumption. So you scan s and you partition it into two parts. Elements, integers which are smaller than x, integers which are bigger than x. Right, and then you recursively sort. So it's a divide and conquer strategy. The analysis does not give you anything interesting because the pivot is kind of arbitrarily chosen. But somehow in practice it is faster than merge sort. Okay, this we have asked many times in the assignment for you to do the analysis. So we'll take this pivoting idea and we will take the idea of its recurrence. Okay, so we'll use the pivot and the recurrence, and we'll adapt it to design select s comma I. So for that, the question is, what kind of recurrence gives you linear time answer? Time complexity on n size input, you want order n. Right, so can you think of an example of a recurrence which gives order n? because merge sort or other things always give something more than n. How can you recurse down to a smaller instance and get this order n? So, well, first example is easy. This, in fact, you have seen in some form in this pre-MIDSIM. So, which is you go to an instance which is slightly smaller, let's say 90% of n. Okay, so if you reduce the instance to by some percentage, some constant fraction multiplied by n, solve that, and on top of it you spend linear time. So the answer of the recurrence is, what is the solution? So this is basically, you are doing n, and then you are doing 0.9 n, then you are doing 0.9 square n, and so on, which is, what is this smaller than? The GP of a fraction, right? That GP will be an absolute constant. So for example, for 0.5, it would have been just 2. And for 0.9, it will be 10 or less, right? So it's an absolute constant. So this is big O of n. So if you reduce the instance by a percentage, then you are allowed to do this recursive design and get a linear time algorithm. But that seems difficult for median finding, right? If you even if you reduce to 90%, there is still 10% remaining. So you have to find median on both to have any chance of computing the median exactly. So you cannot rely on just one answer. You need answer on both parts. So what are the examples of such recurrences? So that's the harder thing to guess. So what will happen if you did both 0.9 and 0.1? And on top of that, linear spending. What is the solution of this? Sorry? Is it O of n? So do it as an exercise that this will not give you O of n. Because this is like merge sort. Okay, merge sort also does a similar thing. It divides into 50-50% and calls both. So there is an extra log n which kicks in. So you will get a similar result here. So this will not work. So that's like example 0. So the correct example which we are interested in is let's say this is an arbitrary example for now. So the important thing here is this is an and this is bn, or I'll call it dn, and you notice that a plus d is less than 1. Okay, so this is so first you divide into 20%, then you have 80%, but you don't call on 80% completely, you call only on 70%. Okay, so a plus d is smaller than 1. So if you do this, then you can show that this will give you order n. Okay, so there is some magic here. So this implies that Tn is order n. Okay, and the proof of this will be very easy. You just, once I have told you that answer is Tn equal to Cn, you just substitute there, and by induction you will see the proof. You just substitute C n by 5, C 7n by 10 plus n, and you can show by induction that Cn is a solution for big enough constant C. Okay, so we want to improve on merge sort, which means that what remains, we will not call on the whole thing, we should call on something smaller. Right? So here, instead of 80%, we'll call on 70%. So 2 calls, but the union of the calls is smaller than n. Okay, so this is what we are targeting. And for some strange reason, it will work. So why it will work, that will depend on the pivot. So what pivot should we choose? Should we use to break S? Into 2 parts. So the part which is less than equal to x, and the part which is greater than x. So since I've already declared that we want to do something like quicksort, so recurrence is that the recurrence has to be of that type which we discussed in the previous slide, and pivot has to be that divides S into 2 parts. And gives you the recurrence you want. Yeah, so this will be even harder to guess. What should this x be? So that the quicksort kind of idea has some chance, fighting chance. Yeah, so right now you cannot see why it will be possible, but let us still try at the nx, which is approximately a median. Okay, so I have to define what is an approximate median. So for a given constant b, and x is called B approximate median of S if the number of elements in the first part, number of elements that are smaller, less than equal to x. This is, so for an exact median, you wanted this to be equal to n by 2, right? But we cannot demand that, because that is the answer we want actually. We want the median to be outputted. So we cannot ask for that. What we still can try is, let's say, this size you want to be around n by 2, right? So between n by 4 and 3n by 4. So you want an approximate median. So for parameter b, we write this as that this size is between bn and 1 minus bn. Okay, so we want this number of elements smaller than x. We want them to be around n by 2 and precisely in this interval, b times n multiplied by 1 minus b times n. Is this clear? This is called a B approximate median in an array. And this condition is equivalent to saying that S less than equal to X is at least Bn, and S greater than X is also at least Bn. Okay, so in other words, I could have also defined B approximate median to be an X such that when you look at the two parts, both are at least Bn. Do you see the equivalence? All you have to show is that the second condition, this S greater than X, implies that S less than equal to X size is upper bounded by 1 minus Bn. But that you can deduce easily. So if the second part is large, then the first part has to be smaller than n minus Bn. Right? So from that you will get the equivalence. So this is what such an element X is called a B approximate median, and unlike the median, it is not unique. Okay, median is a unique X, this is not, because there is a big leeway here. So we want to find such an X, divide into two parts, and then call select subroutine twice. So let us do that. Or so in the sorted S, what we are focusing in this approximate B median is in a range. So this is the 0th one, this is the n minus 1th one, assuming that it's sorted, and X is somewhere in the middle. And this part is called S less than equal to X. And this is S greater than X. Okay, so instead of being exactly in the middle, we are allowing now this range. This is the leeway. So we are allowing X this leeway, and any such X we will consider good. So there is this major question, how will we find this X? Which I will postpone to tomorrow. But suppose you can find such an X, okay, then what is the exact median finding algorithm or exact select S comma I? So let's see that idea first. So how to use this? Okay, so we won't discuss for now how to compute X, but once X is there, how to use it. So the reason why this is useful so we'll use this as pivot once we know it, and we'll do the two recursive calls. So let us write that pseudocode. So compute X, which is B approximate median of S, Um, so this we will see tomorrow how to do this. But we want to achieve this in time order n plus another recursive call on a fraction. Okay, we'll set some fraction, and in a single recursive call, we will compute x. Okay, which is a major claim. We'll see it tomorrow. But suppose all that is done, so let's proceed on top of that. So now you partition. So this we just leave, and then so how fast can you partition? Given S and a pivot, this is how much time? Yeah, order n time. So it is easy to partition because you just have to scan and collect all those elements which are less than equal to x, and you make these two arrays, s less than equal to x and s greater than x. So that partition function will give you. Then, so if s less than equal to x size is I, then what do? Then you return. So select was supposed to output the ith smallest integer in the array, right? If s less than equal to x is of that size, then x is the answer. Fine. This also takes linear time, obviously. It's just a single scan. In a single scan, you know the sizes of these arrays. So simply by that, you know how to check equal to I, and if it is matching, then you return x. X is the answer. That's the easy case. The harder cases now come. So else, there are two cases, whether this is less than I or greater than I. So what about greater than I? What should you do now? So this means that x is ahead of the ith statistic, right? So since x is ahead, what should you do? What should you call? Yeah, so you can forget about the other part. You can just call select on this part. So you call on this part all with I. Okay, so on this first part already you can call select and the same I, because I is present in this part. It doesn't care about the second part. And what happens in the less than I case? This should now easy to guess. So you have to call now on the other part. Correct. So since this first part is smaller than I, so I is not present here at all. It is present in the second one. And in the second one, then you have to subtract by this size. That is the statistic you want in the second part. Clear? So that's the pseudocode with one major part missing in the beginning, how to compute x. But suppose you compute it by some recursive call to a fraction of n. You can now see the recurrence. So the recurrence is Tn is less than equal to order n plus T dn plus T of, so T of what? What is happening here? So here there are two calls, but they will not be made together. Only one of them is made. Which one is bigger call? The one that takes more time? So the maximum you will spend here is 1 minus Bn. Just observe that. Okay. So you either will call on B or you will call on 1 minus B. The bigger one is 1 minus B, so we overestimate. So this is for sure will give you an upper bound on Tn. So tomorrow what we'll make sure is we'll solve the pivot X, we'll find that, and we'll make sure that this Dn 1 minus B is smaller than 100%. Okay.